Hello, everyone. I'm Micah. I'm the host for today's talk on the Tartan Planning series. It's my pleasure today to introduce Negar Mehr. Negar is an assistant professor of aerospace engineering at UIUC. And before that, Negar was a postdoc in the Stanford Aeronautics and Astronautics Department, and she received her PhD in mechanical engineering from Berkeley in 2019. She has a bachelor's degree from Sharif University of Technology, also in mechanical engineering, and her research spans control theory, game theory, and machine learning. And she's interested in developing control algorithms to enable safe and intelligent multi-agent interaction. Negar has also been recognized for her work with a NSF Career Award, the IEEE Intelligent Transportation Systems Best PhD Dissertation Award, and as a rising star in EECS, Aeronautics and Astronautics, and Civil Environmental Engineering. And she won a Best Student Paper Award at ITSC in 2016. So Negar, we're really excited to have you here today. I'd like to welcome you to the floor. Take it away.
Yeah, thank you so much for the kind introduction, and thanks so much for the invitation. I'm actually excited to share some of the work that we've been doing at my lab, Icon Lab at UIUC, for enabling interactive autonomous systems with you all today. Because I think we are living at times which are really exciting times for people like me who work at the intersection of controls and robotics, because autonomous systems are really making their ways into our lives across various applications. From autonomous driving to robots in the space, there are all these emerging applications for robotic systems. And although these applications are all very different from one another, there is one feature that is common among all of them. And that is the fact that in all of them, a robot has to interact safely and intelligently with other agents. For example, an autonomous car has to interact with pedestrians, human-driven cars, or even other autonomous cars on the road. Or when it comes to assembling objects in this space, the hope is that robots would interact and collaborate with one another to assemble objects. So this is really a feature that is required for robotic systems of the future. However, this is still very challenging and hard for robotic systems. And you can get a feel for that and sense that by just looking at the news headlines on how robots have been injuring their human coworkers, or I'm sure that most of you heard about the sad news that autonomous cars resulted in fatal crashes. But this is not just a challenge in human-robot interaction. Interaction in multi-robot systems is also still pretty challenging and hard. Here is a video of Ocado's warehouse, which is one of the online grocery stores in the UK. And I was watching this video and I was like, wow, this is very interesting. Robots are used for picking up and placing objects in an environment which is very structured. The entire environment is made, the entire warehouse is made for these robotic agents to work in it. But just this past July, because of 3 robots colliding with one another and not knowing how to interact with each other, the entire warehouse went on fire and the share price of the company dropped by 6% just because of 3 robots colliding with one another. And this was very interesting to me because I was like, this environment is made for the robots to work at such a setting. So the goal of my research is really to avoid these undesirable outcomes and allow robots to be as social as humans. And to do this, we use tools from various disciplines. First, we start by thinking about how should we control one single robot. And to do that, it's no surprise that we use tools from controls theory. And controls is really the main building block of our method. And of course, to operate in complex environments, there needs to be a machine learning and data-driven component also present in the robotic system. because I'm sure that if you are from a robotics background, you've heard about all the advancements that machine learning algorithms have made in the decision-making process of robotic systems. So we use tools from controls and learning algorithms to think about controlling one single robot. And then when it comes to thinking about the interaction between our robotic system and other agents, we use tools from game theory to think about how should agents account for the impact of their decisions upon one another. So what I'm going to do today is that in the first part of my talk, I'm going to talk about why planning in such interactive multi-agent settings is challenging and how we are thinking about it. And then in the second part, I'm going to talk about why inference and estimation may actually become hard in multi-agent domains. And then if I have time, I'm going to briefly talk about some of the future directions which I think are relevant and important, and I think as a community, we all should be thinking about them. So let me start by planning in multi-agent domains. The theme of the seminar is about planning. And I'm going to first talk about why planning in these multi-agent domains is actually challenging. And I'm going to explain that through a video of a Waymo car that went viral, and I think many of you have seen this, which is the video of the Waymo car that is trying to merge onto the freeway. But because it doesn't know how to interact with other cars, other human-driven cars around it, it fails to change its lane, it remains on the exit lane, and it has to sadly exit the freeway. This happens because the Waymo car doesn't know what is the reaction of other cars to its own actions. It's because the Waymo car doesn't know that if it tries to change its lane, perhaps other cars would slow down and let it nudge in. So the thing which makes it hard to plan in these multi-agent domains is that robots need to be able to reason about the likely reactions of other agents to their own control decisions over time to be able to interact with one another. The Waymo car needed to know that perhaps the likely reaction of other cars would be slowing down to let it change lane. So in other words, what we are looking for is the ability to do joint prediction and planning for robots in these multi-agent domains to succeed in their interactions. And what we are looking for is giving robots this capability to have joint prediction and planning to know what other agents would perhaps do once they take a particular action. But let me explain to you how we are thinking about this and how we are trying to algorithmically achieve this. At a very high level, imagine that we have a number of agents. Some of them are human agents, some of them are robotic agents, and each one of these agents has a task that wants to accomplish. Let's say each agent wants to reach a goal position. Each of these agents is a dynamical system in the sense that they have a notion of a state vector and that a state evolves in time according to the agent's dynamics and control decisions. And each agent has a cost function that they want to minimize, which is associated with the task that they want to accomplish. For example, let's say agent 1 wants to reach its goal position. So the cost of agent 1 is to minimize the distance to the goal while penalizing for collisions with other agents. In general, these cost functions could depend on the states and actions of all the agents, but here for simplicity, I'm just showing the dependence on the state. So the challenge that we face in multi-agent domains is that if you look at every agent, let's say agent 1, the cost that is perceived by the agent is not just a function of the states and actions of agent 1 itself, but also it depends on the states and actions of other agents too, which means that agents cannot minimize their cost function in isolation. They have to think about these interdependencies among agents' decisions and account for that. So we can't just optimize a cost function in isolation for every agent. And the right way to think about, maybe actually one way to think about these interdependencies is through the framework of dynamic game theory, where people have looked into modeling the interaction between multiple agents, where each agent is a dynamical system. And they have actually shown that we can capture the outcome of the interaction among these agents through a concept called equilibria of the game. And one specific form of equilibrium is Nash equilibria, which intuitively indicates that at Nash equilibria, we can capture this joint prediction and planning that we originally started with. So one way to achieve the ability to have joint prediction and planning is to look for Nash equilibria of the underlying dynamic game. And mathematically, what an equilibrium, especially a Nash equilibrium is that at equilibrium, no agent will have any incentive for changing their actions. Because if any agent changes their action from their equilibrium action to be something else, that just results in an increase in their perceived cost function. In other words, mathematically, what this means is that at equilibrium, every agent, let's say agent I, if changes its strategy, if agent I changes its action from its equilibrium action UI star to some other action UI, then it fixes the actions of all the other agents to be their equilibrium actions, which is denoted by U negative I star. Agent I is not going to benefit from that change of its action. Sort of mathematically, these equilibrium conditions are, in fact, a set of coupled optimal control problems that we need to solve, because this inequality has to hold for every agent I. So let's pause for a second and think about the things that we wanted to do. We wanted to achieve joint prediction and planning, and it turns out that Nash equilibria can capture joint prediction and planning that we wanted. And we know mathematically what it means to find Nash equilibria of a dynamic game. However, the challenge is that finding Nash equilibria is hard. Because if you think about it, for robotic systems, which are normally nonlinear dynamical systems, they normally have nonlinear cost functions. This means that finding Nash equilibria requires us to solve a set of nonlinear coupled optimal control problems, perhaps on board a robot, which is often very challenging. And several recent works have looked into different strategies, assumptions, or solvers who are getting around this problem. But although there has been a lot of progress on this front, the solutions that we have so far are not scalable. So we started to think about what can we do to get around this challenge. We have a solution concept, which is very powerful, captures what we're looking for, but it turns out computing that in general is really hard. So we started to think maybe there is actually some structure that is inherent in the typical multi-agent interactions that robots would face, which would make the analysis of these games and finding their equilibria a lot easier. Maybe there is a factor in these interactions which makes them a lot easier to analyze that we are missing. And it turns out that there is actually some structure inherent in these interactions, which makes them much, much easier to analyze. It turns out that these game-theoretic interactions are in fact an instance of a dynamic potential game, which are a lot easier to analyze and study. If you come from a game theory background, you probably have heard of the name potential games because they have a number of interesting and appealing properties. And among all those interesting properties, there is one which makes them particularly interesting for the study of multi-agent interactions in robotic systems. And that property is the following. If a game is a dynamic potential game, there exists a potential function P defined over the entire state and action space of the system, such that minimizing that potential function will give us the equilibrium actions of the original game. This means that if a game is a dynamic potential game, we can find the equilibria of the game by solving a single optimal control problem instead of solving a set of coupled optimal control problems. And what we showed was that we, in fact, proved that multi-agent planning becomes an instance of a dynamic potential game when each pair of agents treat each other symmetrically. Let me try to explain the implications of this theorem and what I mean by agents treating each other symmetrically through an example. Consider, let's say, 3 agents, again, in a navigation setup, where every agent, let's say agent 1, has a cost function, which is composed of a tracking cost, C1TR, that, for example, minimizes the distance to the goal, and some collision avoidance terms like C12A, which penalizes for collisions between agents 1 and 2, and C13A, which penalizes for collisions between agents 1 and 3. We say that agents 1 and 2 treat each other symmetrically if agent 1 penalizes for collisions with agent 2 the same way that agent 2 penalizes for collisions with agent 1. If this property holds, then we say that agents 1 and 2 are treating each other symmetrically. And likewise, if the same property holds for all the other pairs of agents in our multi-agent domain, then we can show that the game is a dynamic potential game, and the potential function of the game is simply the sum of the tracking costs of every agent plus the pairwise collision avoidances of all pairs of agents. And the nice thing about this is that now we can find the equilibria of the game by minimizing this potential function subject to the system dynamics. And because this is a single optimal control problem, we can use any trajectory optimization algorithm that is out there for solving this problem. We picked the simplest trajectory optimizer, iterative LQR, for minimizing this potential function. And here are the type of trajectories that we got in laboratory experiments. We managed to run our algorithm in a receding horizon fashion on agents such as quadcopters. And you see here that the quadcopters managed to change their altitude for avoiding collisions with one another and exhibit these intuitive interactive trajectories. Here's another example again in 3D. The quadcopters managed to change altitude and interact with one another to avoid collisions with each other. This was very encouraging for us because this was the first time, as far as we know, we could run a game-theoretic planner on a system such as a quadcopter in real time in the context of navigation. So we were very encouraged by this, and we were like, how can we extend this? How can we go beyond what we just talked about? So we went back to our formulation, and we were thinking, how can we make our formulation more general? One thing that we were looking for was maybe we actually need to think about constraints in multi-agent interactions. Maybe it is the fact that the collision avoidance should be captured as a hard constraint between the agents. For example, agents 1 and 2 should avoid collisions, and that is captured as a constraint, G12, that both of agents should maintain. And likewise, all the other collision avoidance costs are, in fact, collision avoidance constraints. So the more general setting that we were looking for was more of a constrained set of interactions. Maybe there are other forms of equality or inequality constraints that agents are subject to when they're interacting with each other. This formulation is more general, but the challenge is that to capture joint prediction and planning in this constrained setting, now we need to find generalized Nash equilibria, which are in fact like constrained Nash equilibria, which is of no surprise that they are actually more challenging to solve, because not only do we have to satisfy the equilibrium conditions, but also we should make sure that we satisfy the overall system constraints. Here in this notation, I'm using G bar to denote the vector of all agents constraints. So now we need to solve a set of constrained optimal control problems that are coupled with one another to basically find the Nash equilibria. But luckily, it turns out that multi-agent interactions, even in the constrained setup, become an instance of a constrained potential game, which means that we can find the generalized Nash equilibria of the game by solving a single constrained optimal control problem, which is associated with minimizing the potential function of the game subject to overall system constraints. And again, this is just one constrained optimal control problem, so we can use any trajectory optimizer for solving this. We use Altero because it can handle constraints. And here are the type of trajectories that we get when we use Altero for minimizing the potential function of the game when agents are subject to inequality constraints of the form of collision avoidance constraints. And you can see that the agents manage to exhibit these intuitive trajectories for avoiding collisions with each other. But the main purpose of running this simulation for us was that we wanted to be able to compare our method with the state of the art. So what we did was we generated 100 random initial conditions of this simulation where we have 4 agents, unicycle dynamics models in the 2D plane. And we ran our method and measured the solve time of our method and compared that with the state-of-the-art game solver that can handle constraints. And what we found was that when we look at the histogram of the solve times with our method and the state-of-the-art, we can see that our method is 20 times faster than the state-of-the-art, which was interestingly faster than what we had hoped. And because of this tractability, we managed to run our algorithm in a receding horizon fashion on quadcopters around real human subjects. Here you see a quadcopter navigating around 2 of my students. And this is my favorite moment where my student Anna is hesitant whether to move forward or wait for the quadcopter, and the quadcopter manages to interact and resolve the conflict by moving forward. So again, this was encouraging for us. The information that all the information that we are giving to our human subjects is that we are telling them that you should move from your start position to your goal position. So we were encouraged by this, but we wanted to even go beyond this. In this experiment, the quadcopters and agents are assumed to have a collision avoidance constraint, which is in the form of an inequality constraint. But we were thinking, can we have equality constraints? Can we think of interaction settings which can capture equality constraints? For example, let's say a couple of quadcopters transport an object, which means that they would be subject to some equality constraints. And part of it was also because I was inspired by my favorite movie, Cinderella, since I was a kid. I remember I always had this thing in mind. Can I have some birds like this that can help me? Can I have some crazy flies who basically move things around for me? And anytime I can't find my glasses at home, I'm just like, I wish there were some crazy flies that would fly around, find my glasses, and just bring them to me. So that was kind of like an experiment we wanted to run. We were like, let's say two quadcopters, or two robots in general, are tasked with transporting a rigid object, let's say a rod. Let's say the robots want to transport the rod to its final position with a designated final orientation while they are interacting with humans in the environment. This is an interesting setup because now robots have to interact with others while they have to satisfy and maintain this constraint, which is in the form of an equality constraint, that the distance between the two quadcopters and robots should remain constant and equal to the length of the rod. But it turns out that we can handle these type of interactions too. We ran an experiment. I'm going to play this experiment in a second, where the two quadcopters are transporting the rod around again to my students. And our students are just tasked with moving from their start position to their goal position. And the quadcopters are given a designated final position and final orientation. And here are the type of trajectories that we get. You see that the quadcopters manage to beautifully change the orientation of the rod to interact with humans, avoid collisions with humans, and yet satisfy the task constraints and make sure that they transport the rod to its final position with its final orientation. So we were all very excited by seeing these behaviors, and like, that's great. We are generating these interactive trajectories. So we got sort of inspired to think about other forms of interactions. Going beyond these non-cooperative interactions, we were like, can we think about even more complex forms of interactions, such as interactions you would see in racing? Here is a video of drone racing, of course, when drones are operated by human pilots. But you can see all sorts of crazy complex interactions between the quadcopters. The quadcopters overtake, they block one another. In this setting, actually one of them pushes the other to the boundary of the racetrack and results in a crash in that quadcopter. So it's a very interesting domain if you think about it, because drones exhibit all these complex forms of interactions with one another. So we started to think, can we generate such interactive behaviors in the racing context autonomously? What happens if we let our robots race against each other autonomously? Can we generate interactive trajectories using some of these methods that we have been developing? And it turns out that we can actually cast these interactions again as an instance of a dynamic potential game. It turns out that we can formulate multi-agent racing as a dynamic potential game again, which makes it a lot easier to scale these racing trajectories and racing interactions to a larger number of agents, because potential games are a lot more tractable to compute. And thanks to that tractability, we can run against things on board a robot. I'm going to play the video in just a second, but I'm going to explain how this thing works first. So here we are looking at three agents racing on a racetrack, which is denoted by the white lines. And the ego agent, which is the green agent, uses our algorithm, potential games. And the two other agents are using standard model predictive control algorithms. In the first video that I show, the green agent, which is the ego agent, starts first, but it has a lower speed limit compared to the other drones. And it manages to overtake the blue agent. And then it manages to win the race. And it manages to maintain the advantage that it had at the beginning of the game, which was starting first. So let's just wait for a second for this to be over. In the next round, the ego agent starts second, but it has a higher speed limit. But yet it still manages to, again, overtake and win the game by overtaking the blue agent, which has started first. So it takes advantage of the fact that it had a higher speed limit. It overtakes and manages to win the game. So the takeaway message from all these experiments that we've been running is that we have so far been showing that robots can, in fact, plan in multi-agent interactions and multi-agent domains by leveraging the structure that is inherent in these interactions. And that structure for us has been the fact that these game-theoretic interactions are, in fact, potential games. And that has been encouraging to us. And I think there are still a number of ways that we can extend this and we can take these ideas and proceed with them. But now I want to focus on something which was kind of implicit throughout my talk. And I want to talk about this part too, because I think this is as important as the first part that I talked about. And that is the assumption that I started with, and I kind of implicitly made that assumption and didn't talk about it much in the first part. And that was the assumption that I kind of implicitly assumed that I know every agent's cost function. This is the slide that I started my talk with. And a very natural question to ask is, how do we know agents' cost functions? Let's say if a robot is interacting with a human, how do we know the cost function that the human is optimizing? Or even with robots, how do we know the cost function that robots are optimizing? Or how can we even quantify a cost function for a robot to accomplish a task? The natural and common approach towards cost inference and learning agents' cost functions is through the framework of inverse reinforcement learning, where the idea is we can watch an expert, let's say a human, and watch them how they accomplish a task, collect a set of trajectories of the task execution, and under the assumption that the expert is acting noisily and the expert is noisily optimizing a cost function, we try to learn and recover the underlying cost function of the expert. And this normally is achieved through the framework of maximum entropy optimality, where the idea is that the probability of taking an action at a particular state is proportional to the exponential of the negative cost that is accumulated from that state and action pair. That's the typical assumption in these works, and there has been a lot of progress and there have been a lot of advancements in this direction. However, all these methods assume that we learned from an expert in isolation. So they are good when we want to learn an objective function for a task which does not involve interaction among the agents. Because if that inferred cost function is going to be used in an interactive setup, it fails to capture the coupling among the agents. And it fails to learn a good understanding of what agents' objectives are when they're actually interacting with agents. So our key insight has been that we need to account for agents' interdependencies in the cost learning phase too. If my argument is that I need to account for agents' couplings and interdependencies in their decision-making phase, then we should also think about these interdependencies in the cost learning and intention inference too. Intuitively, if someone wants to know how I would behave when I interact with other agents, they should watch me when I'm interacting with others. And just watching me when I'm sitting in my own room, working with my own computer is not going to reveal how I interact with other agents. So what we've been trying to do has been focusing on how we can learn agents' objectives and intentions from demonstrations of their multi-agent interactions, rather than learning from an agent in isolation. That is what we want to do. And mathematically, what this means is that we need to solve an inverse dynamic game. We need to recover and learn agents' cost functions such that the learned cost functions rationalize the set of demonstrations of agents' interactions as equilibria of the underlying game. So this is a very challenging problem because solving a game in general is itself challenging. Solving the forward problem is in itself challenging, let alone solving the inverse game. But there is even one more challenge that we need to think about. And that becomes particularly relevant when we are learning from interactions of humans with one another. And that is the fact that no matter what we do, there's going to be noise in interactions, and there's going to be noise in our demonstrations of interactions. So we need to think about how to capture noise in agents' interactions, especially when we are learning from humans' interactions, because humans are only boundedly rational, and assuming that humans are perfectly optimizing their cost function and reaching a perfect equilibrium may not be realistic. And this is actually the approach that people, and this is something that has been observed by people in the community of inverse reinforcement learning, and that's why people have developed max-end frameworks to account for these noises. So a natural question to think about is, how can we account for noise in agents' interactions? What is even a notion that we are going to use for this? So I'm trying to address two questions here: how to capture noise in multi-agent interactions and how to solve the inverse game. And I'm going to start with the second question: how to capture noise in interactions. I define a notion of equilibrium that captures noises in interactions, and then I talk about how we solve the inverse game. To capture noises in interactions, we looked into the literature in cognitive science to see how people actually behave in laboratory experiments. These are much simpler experiments in the sense that they are one-shot interactions. Agents make decisions only once. And it was interesting because we observed that there is something called quantile response equilibria, which you can think of them as noisy versions of Nash equilibria that were observed to explain human choices in laboratory environments very accurately. And the idea behind quantile response equilibria is the following. The assumption is that every agent maintains a probability distribution over their actions. Let's say agent 1 has a probability distribution over its actions F1, and then agent 1 computes the expected value of its cost function with respect to the policy of the other agent, with respect to the possible actions that the second agent would take. And then if agent 2 does the same thing, at equilibrium, the probability of taking an action by each agent is proportional to the exponential of the negative expected cost associated with that action. The tricky thing is that these orange boxes should hold simultaneously. So this is a fixed point. F1 and F2 have to jointly satisfy this. But it turns out that such F1 and F2s actually explain human choices pretty accurately in laboratory environments, and they capture noise in humans' interactions. So we were inspired by this, and we started to think, how can we actually extend this to decision-making over time? And how can we come up with a notion of equilibrium that is good for Markov games and noisy interactions in these Markov games? We did that through the notion of the Q function in a multi-agent domain, where, let's say, for simplicity, we have two agents, and each agent I computes the Q function associated with a set of state and actions, which is basically the sum of the costs that will be accumulated starting from that state and action pair. In this notation, Li is the running cost of every agent. Then let's say we compute the expected value of these Q functions for every agent with respect to the policies of other agents. For example, for agent 1, Q1 bar is the expected value of Q1 with respect to pi2, which is the policy of the second agent. Then what we propose as a concept of noisy Nash equilibrium in dynamic decision-making setups, which we call entropic cost equilibrium, is the following. We propose that at equilibrium, the probability of taking an action by every agent I at a particular state is proportional to the exponential of the negative expected cost associated with that state and action of that particular agent. Again, this is a fixed point. This has to hold for every agent I. And the interesting thing is that you can actually verify that this recovers the maximum entropy optimality principle when we have just one agent. So if we just set the number of agents to be one, this gives us the maximum entropy principle that is the underlying foundation of all these inverse reinforcement learning papers and works. So there is that connection. And we actually formalized that connection to maximum entropy principle. And we showed that these entropic cost equilibria are in fact the equilibria of a game in which every agent is not only trying to minimize the running costs at every time step, but also try to maximize the entropy of their policy. So there is this entropy term here in the running costs of the agents. And if you look at the equilibria of such a game, this gives us the entropic cost equilibria. So if you think about it, it's very natural because now we're saying that maximum entropy principle is when agents also try to maximize the entropy of their policy. Here we are saying the same thing. We're saying entropic cost equilibria are the equilibria where agents are also trying to maximize the entropy of their policy. And leveraging this connection, we can show that if a game has a structure such as linear dynamics and quadratic cost functions, these entropic cost equilibria can in fact be found in closed form, which enables us to approximately find the forward solutions or these entropic cost equilibria for general nonlinear games. I'm not going to talk about the details of this, but there is one thing I want to highlight about an interesting property of these entropic cost equilibria. And that is the fact that if we consider more general forms of these entropic cost equilibria, where we have like a weight parameter like beta I over the entropy term in the running costs of every agent, then we can interpret this beta I as the level of rationality that agent I has. And as beta of I increases, the agent's irrationalities increase. To just give you a sense and some intuition for that, let's just look at the trajectories of two agents that are interacting with each other under this entropic cost equilibria as we increase beta I. You can see that as we increase beta I, the level of noise and interactions and the trajectories of the two agents increases. So far, I have addressed the question that I talked about, which is how to account for noise in the agent's decision-making process. So I know how to quantify that, and I know how to compute these entropic cost equilibria, but I still haven't talked about how we solve the inverse dynamic game to enable cost inference. So now, let me tell you at a very high level how we get around that part, inverse solution of these dynamic games. We do that by leveraging an assumption which is very common in the inverse reinforcement learning literature. And that is the assumption that the running cost of every agent is a weighted sum of a set of a priori known features, phi's, which could be general nonlinear features of the state and actions of all the agents. And we learn the weight parameters such that the expectations of these features, phi's, under demonstrations of interactions are roughly the same as the expectations of these features under the entropic cost equilibria of the learned weight parameters. And the intuition behind this is very simple. We don't know the ground truth objective functions that agents are trying to optimize. when we're trying to learn from their demonstrations. So what we're trying to do is that we are going to make sure that the trajectories under the learned cost parameters look roughly the same as trajectories in our demonstration data set. That's basically the intuition behind this. And we have been running this algorithm and using this for verifying whether we can actually learn more accurate objective functions by accounting for these interactions in a number of simulation studies. I'm going to skip these details in the interest of time, and I'm just going to talk about one experiment that we ran with actual real-world data of human drivers using the interaction data set. We considered a merging scenario in a highway in China, and we collected a number of trajectories for the vehicles. And we sort of decomposed these trajectories into our training data set and our test data set. And we used our training data set to learn the weight parameters for the merging vehicle and the vehicles on the main line, and use these learned weight parameters on our test data set to predict the trajectory of the vehicles and compare those trajectories with the actual trajectories of the vehicles and measured the prediction accuracy as a measure of how accurate our learned cost functions are. We did the same thing with the state-of-the-art single-agent inverse reinforcement learning where each vehicle treats other vehicles as moving obstacles. And we also compared them with intelligent driver model as a baseline for driving, because IDM, intelligent driver model, is known to be pretty accurate for driving scenarios. And here are the type of results that we get. On the y-axis, you see the position error in our prediction, and the x-axis, you see the time. You can see that our method, multi-agent inverse reinforcement learning, is actually a lot more accurate in terms of predicting agents' trajectories compared to single-agent inverse reinforcement learning. And interestingly, over long horizons of time, it is even more accurate than intelligent drivers model. IDM is really tailored for driving. It is developed for modeling driving. It has a number of parameters, and all those parameters have been tuned and optimized. And yet we managed to even beat IDM for longer horizons of time. So verifying things with actual human drivers data sort of confirmed our hypothesis that in fact, we can learn more accurate understanding of agents' intentions for interactive tasks by trying to learn from demonstrations of their multi-agent interactions rather than learning from agents in isolation. So with that, I want to spend the remaining few minutes on a couple of things that I think are important to think about. And I want to start by something which I think is really important and I didn't really get a chance to talk about, and that is the safety aspect of these interactions. So far, everything that I talked about in this talk was very deterministic. The dynamics were deterministic. But when there is uncertainty in system, some noise in the system, here is what happens to your robot. The robot gets confused. It doesn't know how to plan and move forward because the amount of uncertainty is the system is just too much and it can't handle those. And a natural question to ask is, how can we think about safety in these uncertain domains? And this becomes even more challenging when uncertainties in the system have an unbounded support where we can't just use worst case analysis. So we've been thinking about this, and one idea that we have been exploring, which seems very interesting, is to enable robots to take advantage of a notion of a risk measure for avoiding potentially unsafe rare events when they are interacting with one another. So we want robots to be able to assess the risks that are associated with their actions when they are interacting with other agents. And this is consistent with even what the policymakers have observed in terms of issuing policies and orders for deployment of autonomous cars. For example, Arizona governor issued an order which allows autonomous cars to be used without human operators only if they satisfy some minimal risk conditions, which means that we want these systems to be able to quantify the risks that are associated with their actions. And we have been considering that idea of maybe it is the fact that each agent in an interaction domain where we have uncertainties is in fact a risk-averse agent. And we are trying to come up with strategies which enable risk-aware agents to interact with each other, because it turns out that by thinking about this risk awareness in interaction, you can have interactive agents that react to the level of uncertainty in the system. The more uncertain the system gets, the more conservative the agents get too. So I think there are a lot of interesting problems to look into in this domain to make sure that interactions are going to be safe. But there is one other piece that I want to talk about, and that is the fact that although we've made a lot of progress in enabling multi-agent interactions, we're still far from exhibiting and showing all forms of complex interactions in robotic systems. Because if you think about it, we as humans are capable of accomplishing various forms of complex interactions. We as humans are good at scalable interactions. We can collaborate with our partners in very safety critical and challenging environments. We can even coordinate with our teammate while we are competing with another team. So we have this hierarchy of interactions that we are really good at, and our robotic systems are not there yet. So there is still a lot of, there are still a number of challenges that we need to face to make robotic systems capable of exhibiting these complex interactions. And one thing that we're excited about is that this reduction of interactions to one single optimal control problem through potential games that I discussed enables us to apply all the tools, the techniques that have been developed for single agent planning to multi-agent planning domain. For example, we can apply distributed and decentralized optimization techniques to the problem of minimizing the potential function to enable scalable interactions. We are thinking of applying tools from online optimizations to adapt to enable adaptive interactions, and we can learn online from agents that we are interacting with. So I'm hopeful that this reduction at least enables us to make progress in the direction of achieving complex forms of interactions. And finally, I would like to end by something which I think is really important, but is oftentimes overlooked in the community, and that is the societal scale implications of these interactions. Let's say we will be living in a time, hopefully in the future, where autonomous cars are deployed at a large scale on road networks. Then these systems will be interacting with humans, will be interacting with human-driven cars at a system level, and then they'll have system-level impacts that we must be aware of. Because if we think about the societal scale implications of these systems, then maybe we can have, for instance, autonomous cars that act altruistically and choose their routes, for example, in the favor of the society to minimize congestion in the network. And we can, for example, have drones that when they are used for delivering packages, they are being deployed in a way that they minimize congestion in transportation networks, and they act in the favor of the society. Because then, once we have altruistic interactive autonomous systems, we can make sure that everybody is benefiting from the presence of these systems and these technologies in our lives. So with that, I would like to thank all my students who actually did the work that I got the credit to present today, and thank all the funding agencies who made this work happen by their support. And I would like to thank you all for your attention. I'd be happy to answer any questions you may have.
Thanks a bunch, Negar. I really enjoyed listening to your talk right now. So for the question and answer session, we have a few questions that I've seen on the YouTube stream. And I'll read a few of those off. I see a question on the Zoom chat, and I'll probably ask a couple questions myself. I think I'll start with this question from YouTube by Abhishek Gadar. So he was asking about your formulation for potential games. Does that require like a densely connected interactions in the graph, or can you have a sparse graph and then potentially exploit that kind of structure?
Yeah, that's a great question. In fact, I think that is something that we have been exploring, because you don't need a fully connected and dense graph. All you need is that if there is a connection, that connection is symmetric in the potential game formulation. And I want to just go back to this slide that I started with. Here, to make these interactions scalable, we are in fact using and leveraging the property that you just mentioned, because not every agent is interacting with all the other agents at every time instance. We managed to distribute this and make these a lot more scalable. So this applies to sparse graphs too. All we need is that once there is a connection between the two agents, it's a bidirectional connection and it's symmetric. But the good news is that right now we have some ongoing work in my lab where we show we can even extend that symmetry assumption and make things asymmetric too in terms of the weighting in the cost functions. But we don't require the graph to be dense. That's a great question.
Okay, thanks, Negar. So I think I'll ask one of my own questions right now. So you talked a little bit at the end of the talk about societal scale interactions, altruistic autonomy. I saw a little bit of that on your website, and I want to dwell on that a little longer. And maybe you could tell us a bit about how these ideas developed for you and why you think they're important.
Yeah, that's actually an area that I'm very excited about. And I'd be more than happy to give another talk on that subject itself. But really the thing that we think about, which again, as I said, I think is sometimes overlooked, is the fact that these systems will be interacting with humans at a system level. And humans at the end of the day are strategic decision makers. They adapt and change their behavior once autonomous cars, let's say, are there. Let's think of it in the context of transportation, because that's the most foreseeable form of system level interaction between autonomy and humans. So we often assume that humans' behavior is going to be fixed. And then we're like, okay, great. If we replace human-driven cars by autonomous cars, things are going to be great. But the part that is sometimes overlooked is that humans are going to change their behavior once autonomous cars are around. I may not take the usual route that I take with my own car once I'm having an autonomous ride. So people would change and adapt as autonomous systems are here. And I think it's when you think about trying to understand and modeling how humans would adapt themselves and change their decisions once autonomous cars are present, you would see that these actually will have very complex behaviors, which sometimes may even be unintuitive. For example, let's say everybody starts using autonomous cars because they're cheaper and then they are a lot more fun. Then maybe that even results in an increase in congestion. Who knows? Maybe certain things would get better, certain things may actually get worse. In our work, we have shown that because of how people change their decisions and, let's say, route choices in a transportation context, when autonomous cars are around, for certain network geometries, the congestion may actually get worse. So the thing which I think is important for all of us to think about is when we think about applying and deploying these autonomous systems, what type of control strategies and policies can be put in place when controlling and using these systems, such that these unexpected behaviors that result from how humans adapt themselves to these systems would actually be avoided, and make sure that these systems are benefiting the society. And the typical example that I give is, let's just think about what happened 100 years ago. Cars were invented, we were all very excited, and we started adapting cities to cars rather than adapting cars to cities. And then we ended up with congestion, air pollution, safety issues all around the world. now that we are ready for having autonomous cars around, how can we make sure that the same thing would not happen? We all get very excited about autonomous cars, and then in 50 years, we end up with cities that are, filled up with congestion of autonomous cars or some other aspects we haven't thought of. So I think it's important to be proactive at this time to make sure that we are not going to repeat the same mistakes we made 100 years ago when cars were invented.
Thanks, Negar. I really like that last point about how we can design our cities and society and how we've made mistakes about that in the past. At this point, I think I want to switch to a question from Zoom. We're also a few minutes over. I think I'll let us go on for a couple more minutes in questioning, if that's all right with you. So Jacob Willits had a question on the combinatorial nature of these systems and what happens when they scale to a large size. So Jacob, I'm going to unmute you now. Let's see. I'm going to try to unmute.
I think I can read Jacob's
okay.
question. Yeah, and that's actually a great question, Jacob. To elaborate a little bit on the points that you mentioned, like you said, multi-agent planning is in itself combinatorial. And when we were thinking about the complexity of our algorithm that leverages potential games compared to game-theoretic solvers, we found that the complexity of our algorithm is linear in the number of agents, while the state-of-the-art is cubic in the number of agents. So that enables us to run things with more agents compared to the state-of-the-art. But one interesting thing, but that still doesn't mean that we can scale our method to like an arbitrarily large number of agents, right? So one of the things that we're, like I said, we've started to explore is that because first we are having some savings by going from cubic in the number of agents to linear, but still our method is going to, the complexity of our method increases with the dimension of the state space. So the complexity with respect to the dimension of the state space remains the same. And that's the part where we are looking for using ideas from distributed optimization and decentralized optimization to make things more scalable. Because now I can readily apply all the techniques that have been used in, let's say, decentralized systems and distributed systems to make these more scalable. And so far, out of experiments that we've been running, we've seen that we can run, for example, with quadcopters, we can handle like 6 to 10 quadcopters still in real time. I haven't included the videos of those in this slide here, but we can definitely go beyond 3 or 4 agents, up to 10 agents. But it depends on the complexity of the dynamics of the agents too. If the agents dynamics are simpler, we can even go beyond that. But really the challenge is that what we've been doing is addressing the complexity with respect to the number of agents, but it's still the dimension of the state space keeps increasing as we increase the number of agents. And we've been trying to look for tools from distributed optimization to get around that and hopefully make things more scalable.
Okay, thanks. I'm going to ask a question from the YouTube chat from Wenda. So she was asking if you had considered using graph neural networks in decentralized settings and whether you can learn communication between agents.
Yeah, that's a great question. And that's actually a very interesting idea that we've been thinking about. All these works are very recent, and I'm very excited about this because, like I said in this slide, now you can apply everything that we know from like multi-robot systems, graph neural networks, communication strategies. You can apply all of them in this context. For now, we just assume that every agent gets to communicate with everyone in a particular radius around them. But you are pointing to a very interesting problem to look into, which is learning the communication strategy for these agents. And that's definitely something worth investigating, and we haven't done that yet.
So talking about the recent works, I'll ask one question I had, which is, so in your talk, you started out with like game theory and control, and then moved on to topics related to reinforcement learning. And I was wondering how much of that is relevant to like a linear, like a temporal progression in your work. And if you were to like go back to maybe some of your earlier works and revisit those, if maybe you would do some things differently, or how's your perspective different now?
So seems like for some reason I couldn't hear you well. Do you mind repeating your question so that I make sure I know what you're asking about?
So it, like, I guess especially in references to ideas from machine learning and reinforcement learning, if you were to go back to your earlier works, maybe based on what you've learned and how your perspectives have changed, like what might you do differently now?
So actually one of the things, so I spent a lot of time looking into the literature, especially in IRL literature, trying to figure out what's going on in the area. And I think one thing that I really learned as part of that experience is to just step back and zoom out and try to first understand the fundamental of the problem and then try to address that. And I think looking into the literature, one of the challenges is that there are a lot of works, and you need to keep track of what everyone has been doing, what everyone is up to, and then figure out how they actually map to your work. So if I want to, at a very high level, what I would do is that I would not be too worried about catching up with everything, and first make sure that I understand the fundamentals of things, and then see how they actually transfer to my problem domain. And I'm sure that would have saved a lot of time on my side. But just one, perhaps more of like a technical comment on the inverse reinforcement learning piece. I think there is a lot of opportunity and room for solving these and thinking about cost inference, intention inference in the multi-agent domain. That has typically been done in just a single agent domain. But if you think about it, there are certain things which only become meaningful if you try to learn from multi-agent interactions. For example, imagine you're a robot and you're trying to figure out who is the leader of a team, who is the follower of a team. What is the role of every agent as part of a team? Are there even one team or two teams in the set of agents that you're interacting with? Who is the best agent for you to collaborate with? We as humans are really good at inferring those, but we should have robots that are also good at inferring these capabilities so that we can have like a natural and seamless interaction of robots with other agents. And those can be achieved only by looking at agents' interactions. You can't know who is the leader, who is the follower, if you just try to learn from an agent in isolation. And you could even think about learning costs functions from constraint functions from demonstrations of interactions. And all these interesting problems that come up, I think those are really interesting to think about. And the more I sort of started digging into this literature, the more I was convinced that there are actually a span of problems that one could think of when thinking about intention and objective inference in these multi-agent domains.
Okay, thanks, Negar. So at this point, I don't see any new questions, and we're about 10 minutes over. So if you have anything, like any last words you want to share, maybe you could say that now.
Sure. So once again, I want to thank you for the invitation. This was really fun. And if anytime you had any thoughts or ideas on how to make autonomous systems capable of safely and intelligently interacting with others, feel free to send me an email. I'd always love to chat and brainstorm on ideas.
Thanks a bunch, Negar. Really enjoyed having you here today and chatting with you, and I'm sure our audience did as well. Yeah, so I think that brings us to the end of the talk.
Thank you, everyone.